Jeremy Blum here with Arduino tutorial number 4. We're on a roll here. Today we're going to be talking about analog inputs to the Arduino. I'm going to talk about setting a reference level for the analog voltage, taking an analog voltage in from either a pre-made sensor or building one yourself using a variable resistor and a voltage divider, which is something we talked about last week. And then we'll talk about mapping those values to different values in the Arduino programming language, using it to control LED brightness, which is an analog output, and a few other applications. So let's get started. Let's talk a little bit about how analog inputs are set up on the Arduino boards. Here I have the Uno, the Mega 2560, and the Nano boards. All of these allow for analog input options, and on all Arduinos there is a 10-bit analog digital converter that allows you to convert from ground up to the input voltage of the Arduino, usually 5 volts, to a value from 0 to 1023. That means you have 1024 bits of resolution, or 2 to the 10th power, hence why it's called 10-bit resolution. If you want to learn a little bit more about how analog digital converters work, please watch my TechBits episode on analog and digital signals. You can set the reference voltage that you use for the analog inputs on all these Arduino boards. By default, it's set to 5 volts or 3.3 volts on 3.3 volt Arduino boards, but here we'll just be working with the default 5 volt boards. You can also set it to an internal 1.1 volt reference, although that's not available on the Mega. And on the Mega, you can use different commands, set it to 1.1 volts or 2.56 volts as a reference. You can also set your own voltage reference by setting it to an external value, which you input into an analog pin on the Arduino. Here we can see the analog reference pin that I was talking about. You might want to consider using an external analog reference if you're only using sensors that go from 0 to 3.3 volts on a 5 volt Arduino. The reason for this is that the values from 3.3 volts up to 5 volts, if you use the default 5 volt reference, will basically be excluded and you'll be getting less resolution than you potentially could. Using an external voltage reference allows you to eliminate that problem. Down here on the bottom we can see the analog inputs, A0 through A5. There are 6 inputs available on the Arduino Uno. If we look now at the Mega has many more analog inputs available. All these right here. Analog input 0 through 15, so there's 16 analog inputs available on the Mega. And if we look at the Nano board, we can see that there are actually 8 analog inputs available on here. For our first sensor, let's use a simple photoresistor. Photoresistors simply decrease their resistance as the ambient light in the room increases. As I decrease light in the room, the resistance will increase. So if we hook this up in a voltage divider circuit with a fixed resistor, we can essentially feed into the Arduino a voltage that varies with light in the room. So let's hook that up using this schematic. Here's our assembled circuit. Just like in the schematic, we have a photoresistor connected between 5 volts and a 10K resistor. The 10K resistor then goes to ground, and at the junction between the two of them, we take a wire out and go to analog input 0 on the Arduino. This is just like our voltage divider setup that we worked on in the last episode. Now let's program this to show us the values from the photoresistor as we change light in the room. Note that you can change the position of the photoresistor and the fixed resistor, and the values in the computer will inverse. Let's write a quick program that will show us the value of this sensor. So first we'll need to define our input pins. We'll call it sense pin. That's going to be equal to analog input on pin 0. Now we always want to do our setup function. And in here we don't need to define it as an input pin because it's set to that as default. We can define the analog reference as default. That's because we're going from 0 to 5 volts. But again, this line isn't necessary. It will do this by default. But I'll just put it in here for complete coverage. And we'll want to print this to the screen, so let's set up our serial connection like we did last time. And the 9600 just means the speed at which we're communicating with the computer. 9600 baud is a pretty common value that you use. Alright, and in our loop, all we're going to do is read the sensor and then print it to the screen. So serial.println, just like last time, analog read, and the sensor pin. Sense pin. Make sure we close our parentheses. And we don't want it to spit out values constantly, so we'll just put a delay in there of a ½ second. That should be good. Alright, let's see how this works out. So we can see that in ambient light we're getting a value of about 950. And as I put my hand over the sensor, we can see that drops down. If I cover it completely, we go down to about 750-ish, 770. Okay, great. But that's only giving us a range of 200 out of a potential range of 1024. Why is that? Well, it's partially because of the resistors that we've chosen and the inherent fact that you're going to lose some values by using a voltage divider, which is fine. We don't need the full 1024 of resolution. You can overcome this by setting up an op-amp and doing a few other things, but it's not really that important to us. If we want, we can try to change the resistor to a 1K resistor and see how that changes it. Now we've got a 1K resistor in the circuit instead of a 10K resistor, and we can say let's change the values. Now ambient light is closer to around 570, and if I put my hand over it, it drops down to about 200. So that range is a little bit better, not by much, and you can keep messing with the resistor values until you get a value where you're happy. But in reality, this amount of range is fine for what we want to do. We just saw that a value of around 900 is ambient lighting in the room, so let's make a simple night light now. If the value goes below 800, we'll turn on an LED that will illuminate the room. So all I've done here is add an LED to our circuit with our 150 ohm resistor, same as we used last time, and I've hooked it into pin 9 on the Arduino. So let's go program that. Alright, the first thing we'll have to do is to add our LED pin here. And that's going to be pin 9. Next up, we have to set that pin as an output because it defaults to an input. So let's make the LED an output. And we can get rid of the serial communication. We're not going to use that anymore. Okay, down in our loop, let's start by getting the value from the sensor and saving it to a variable. So we'll make a new variable called val. Pretty standard name. Do an analog read of the sense pin. We don't need this one. We don't need either of these anymore, right? And then if the value is less than 800, we'll do something. So we'll use an if statement, which checks the value. So if the value is less than 800, we will do a digital write to the LED pin and turn it on. Otherwise, if it's greater than 800, let's make sure we turn it off. Digital write LED pin low, which will turn it off. And that's it. So let's see how this works. Okay, great. We put our hand over it and the LED turns on just like we want it to. When it gets too dark in the room, we'll have a nightlight now. Now you don't have to be afraid of monsters in your closet. Now let's make our nightlight a little bit more adaptive. We'll have it change brightness based on the brightness in the room. As the room gets darker, the LED will get brighter to illuminate the room better. We're going to need to do a few things to do this. First off, we need to map our value. So there's a function in Arduino called map. And map takes in the original value, val in this case, and values to map it to. So the reason we do this is because our value for an analog input can range from anywhere from 0 to 1023, whereas analog output, what we'll be using to change the brightness of the LED, is only 0 to 255. Additionally, we want an inverse relationship. As the value from the light sensor increases, we want the value on the LED to decrease, and vice versa. So the map function will allow us to do that. Val is the function we want to map, and let's say we'll set 750 as the minimum and 900 as the maximum, and that'll map to 255 and 0. And we'll set that new value equal to LED level. So precisely what this is doing is it's taking in val from the sense pin. The value of 750 gets converted to 255. The value of 900 gets converted to 0. Anything in between scales proportionally. So as the value increases from 750 to 900, this value will decrease, or LED level will decrease, from 255 down to 0, which we can then feed into our LED to change its brightness. We want to do one more thing though, which is to check for values outside of 750 or 900. If it's less than 750 or greater than 900, we want to set it equal to those values so that we're not dealing with anything greater than 255 or less than 0, because the analog output won't know how to handle that correctly. So we'll use one more function, and we'll reset our val first using constrain. Constrain is another Arduino function that takes in a value and then sets minimum and maximum values. So we'll set it to the same values, 750 and 900. Now what this does is takes the value from our sense pin. If it's less than 750, it resets it to 750. If it's greater than 900, it sets it up to 900. Now we only have to worry about values between these two, which means these values will always be between 255 and 0, just as we want them to. Now we can get rid of this and just use analog write to set the brightness of the LED directly. Analog write LED pin, and we'll now set it to LED level. Awesome. Let's see how that works. Okay, so the LED starts off like we expect it to. And as I move my hand closer, we see the LED incrementally gets brighter until it's at full brightness when I have the sensor in complete darkness. And it scales back just the same way. Perfect. We now have an adaptable nightlight. Naturally, photoresistors aren't the only kind of variable resistors that you can use in a circuit like this. Here I have a thermistor which varies its resistance with temperature. As I hold on to it, you can see that the value drops from 460 down to about 440. So this is actually working in the opposite direction of the photoresistor. If we wanted it to increment the values in the same direction as the other one, we could swap it with the resistor. Another thing to experiment with is using different resistor values. If you look at the voltage divider equation that I showed you in the last episode, you'll see how setting this resistor will affect the range that you get the analog readings on. And then of course you can also use op amps to scale the readings up so you get a better resolution, but we won't cover that in this episode. Of course, you don't always actually have to build your own sensor. You can often buy pre-assembled sensors that are designed to output at a certain voltage, so you don't have to worry about scaling them or adding a voltage divider circuit or anything like that. This is an example of one. This is an infrared distance sensor. It uses an infrared emitter and receiver to bounce infrared light off an object and detect the distance to it. All sensors that come like this will usually have 3 wires, a voltage wire, a ground wire, and a sense wire. The red wire, we give it 5 volts. Ground gets connected to ground, of course. And then the yellow wire returns a value between 0 and 5 volts that we can feed into the analog digital converter in the Arduino and use it to measure a distance value. You'll often notice that these kinds of sensors will give you a broader range because they've already designed it to operate on the whole 0 to 5 volt range. You can also buy these sensors in 3.3 volt iterations and other voltage versions. So if we look at the screen now, as I move my hand closer and closer, you can see that the value slowly increases from about 50 all the way up to about 600 something. Let's wrap up today's tutorial with our first little project. This project will combine the infrared distance sensor and the photodiode that we used today to make an emergency lighting system. In the event that a room is dark, detected by the photodiode, and movement is detected by looking at values from the infrared distance sensor, we'll turn on our emergency lighting system, in this case an LED. Although you could easily hook this up through a relay to control a more powerful bulb. A lot of the code we'll be using to make this system work is very similar to what we had before. There's only a few modifications that we need to make to put everything in place. The first thing is we're now using 2 analog inputs, analog input 0 and analog input 1. 0 is connected to the distance detector, or in this case a motion detector, as we're using it, and analog input 1 is connected to the photodiode, which I'm calling light pin. We still have an LED connected to pin 9. Next up, we're going to need to make 2 variables to keep track of the distance. What we'll do is every time through the loop, we'll look at what the distance is from the infrared distance sensor and compare it to what the distance was last time. If it changes significantly from the previous detected value, we can assume that something has passed in front of the infrared distance detector and assume that movement has occurred. So we'll use these 2 variables to track that in the loop. Our threshold, defined by int thresh, I've set it about 200. This is basically the value for which it's looking for a deviation amount between the last distance and the current distance. You can fine tune this to make the system as sensitive or as insensitive as you want. I found that 200 works pretty well. Setup is the same. We just have to configure LED pin as an output. Everything else is defaulted. And here's our loop. So first off, we're going to read our light value in from the photodiode using analog read, just like we did before. and we'll read in our current distance from analog read motion pin. Note that here I have to define light val as an int because this is the first time I'm using it. Current distance I've already defined as an int up here, so I don't need to use the integer term again. The next thing we're going to do is look if everything meets our conditions. So this if statement will check if the threshold has been exceeded and if the light value is less than a value of 800. So how are we doing that? Let's break it down. There's two parts here, the part in this set of parentheses and the part checking for the light value. Those two parts are separated by double ampersand, which is a logic AND. That means if both the contents of this parentheses are true and this is true right here, then we'll execute the if statement, which turns the LED on for 1 second. If we look more specifically into this part of the if statement, we can see that we're checking for our thresholds. These double pipes indicate a logic OR, so either this or this has to be true for this entire part of the if statement to be validated as true. The first part, before the double pipes, says current distance is greater than the last distance plus the threshold. So if our threshold is 200 and our previous distance was 300, then if current distance is more than 500, then this will evaluate to true. Alternatively, it'll evaluate to true if the last distance was something like 500, and then that minus the threshold of 200 is 300. So if current distance was less than 300, that would also indicate a significant change, and that would also evaluate this to true. So if one of these is true and then this is true also, then we'll digital write the LED to high and turning it on. Leave it on for 1 second to make sure people have enough time to find their way. It'll stay on if it continues to detect movement. Otherwise, we'll turn the LED back off. And then the last thing we have to do is set last distance equal to current distance, so that the next time through the loop, we can compare the distance that we used this time through the loop with the new distance. So if I just put my finger over the photodiode, or I just make some motion, the LED won't turn on. But if the room is both dark and motion is detected, the LED will turn on for a second and help anyone who's roaming through the dark find where they need to go. Thanks for watching this episode of my Arduino tutorial series. If you have any questions or comments, or if you want to watch the other videos in this series, you can do so on my YouTube channel, SciGuy14, on my blog, jeremyblum.com, or over at the Element 14 Arduino group. I hope you guys enjoyed this, and I'll see you guys next week. Thanks to Element 14 for helping me to sponsor this video series. They were kind enough to provide a lot of the materials that I'll be using to create these tutorials. Feel free to go visit their website at element14.com. Check out their community, which is a great place to talk to people about electronics, the Arduino, and basically anything else engineering related. And they also have a store where you can buy a lot of the parts that we'll be using in these videos.